Thank you for the introduction. I just said, let me take about 5 or 10 minutes to summarize quickly what I did last week before going into this slide. Okay, last week I introduced a little bit of quantum probabilities. So what happened is this: whether Albert Einstein liked it or not, it was confirmed that quantum mechanics is intrinsically random. That means at any given time, in its dynamic, the motion, the position or energy cannot be found with certainty, as opposed to Newton mechanics. Then the main issue is how to find the probability that, let's say, the electron is in some area of the phase space R6. Of course, if you know the equation, you need to know the equation of the dynamics, and that will be the Schrodinger equation, the counterpart of Newton's second law of motion. Okay, for that, two main postulates are first provided. Number one, from Neumann himself, that the state of a quantum system, for example, the motion of a photon or of an electron, is represented by a unit vector in the Hilbert space. That's the first postulate. The second, the probabilities, how you find out the probability, you cannot find a position, you can only guess the probability. So how to find the probabilities for an electron? And the second postulate is called the Born rules. A Schrodinger equation that we mentioned last time provided the wave function equation to find out the probabilities. The Born rules say the following: at a given time, the probability of finding the position of an electron is equal to the square of the wave equation, wave function of the wave equation. And that is the rule, it's a postulate. The question is, make sure that in physics, we are not concerned about theorem, we're concerned about equation. And where the equation come from your head. You think about it and you try to see whether or not experiment can confirm. So there are two postulates that we can consider as foundation of quantum mechanics. And then how about, just like a quantum classical probabilities, as Kolmogorov laid out for us, based on the analogy of game of chance, that you go to gambling, that's why they define. And we saw last time, quantum events are projections in the Hilbert space. So if a quantum event is not a Boolean event, it is a projection, so it forms a lattice and not a Boolean, it's not a Boolean algebra. That means it is a structure which is non-distributive and non-commutative, because project just like a matrix is. Think about an event is a matrix. So if you multiply two matrices, they are not the same. A multiplied B need not be equal to B multiplied by A, non-commutative. Okay, and if you look into that in the logic structure, the law of logic is not distributive. We will see that in a minute. That even quantum probability is an extension of classical probability, as we showed last time. But its calculus is very different. So today I will talk about a third postulate for quantum probabilities. That is called the Luder rules. Luder rule is just like a Bayesian rule. It's an update. That means if you see a position and you measure that position, then you change the system. What is the next one? That is called the Bayes rules. So the Luder rule is a basic for talking about something called conditional quantum probability that we mentioned today. So roughly speaking, the Luder rules is an updating procedure, counterpart of Bayes rules in statistics. So suppose that at time t, the system is in a state row. and an event A occurs. Questions: what will be the new system, state of the system? Something happened. What happened to the station? The rule state that the system will be in the state given by a formula that we will discuss in this talk. So the foundation of quantum conditional probability, the topic of today, is based on Luder rules. Attention, a law, a postulate, or a rule are not theorem. They are something that someone think about it and then test, confirm. It consistent with what we observe. So in logic, so we're talking about logic in quantum system. Besides, in order to do calculus, remember in mathematics, Ajahn started it. How you prove a mathematical theorem? What is the technique to prove? There are only two.
You use idea?
Proof by induction and proof by contradiction. That's only two things. Okay. There's a logic. I don't know that you take a course in logic or not. But when you do mathematics, you use logic in order to prove your theorem. Proof by contradiction or proof by induction. However, there's something missing in the current literature about the logic underlying the mathematics that you know very well, which is called a functional analysis. There's something missing right now in the literature. So my contribution today is giving the solution for that missing thing. If you have time, you go on Google and click on the title of what I'm doing here, you will see in it. It just appeared last year at the test conference in Chiang Mai University. So let's go to the slide and go slowly. Make sure that I will go a little technical, but doesn't matter. As usual, I will make sure that you will have something to take home. That's number one. Number two, interrupt me and ask me any question during my talk. Or if you don't like it, you can do it at the end. We will try to have enough time for questions. So the topic of today is conditional quantum probabilities. And mainly, the mainly thing is implication operator. What is the operator in mathematics that you do every time? You know the following. If a function is differentiable, then it is continuous, right? It is your theorem. If the function is derivative, then it is continuous. Okay. So if you want to show that if you find out a function which is not continuous, then what do you get? That means the function is not differentiable. Okay, so that is what we do every time in mathematics. And we need to do the same thing when we do in mathematics, in quantum mechanics, when we have uncertainty involved. So that the topic is quantum probabilities and implication operator. So let me start out. Okay. So there are two main related issues in mathematics, especially in quantum mechanics: probabilities and logic. Both spelled out by von Neumann in 1935. He did both. Of course, not complete. As Richard Feynman famously said, I think it is safe to say that no one understands quantum mechanics. Then what? We need to understand. So how the physicists need to understand this to make your iPhone. But who held them? We, mathematicians. We held them two things. They only designed a system. We held them with the mathematical foundation of quantum mechanics, which is called functional analysis. And we want to hold them with the logic for reasoning. And that is called the quantum logic. And that's the topic of today. We talk a little bit about the concept of probabilities last time. Now we talk about the concept of logic. Okay. Okay. So we talk about logic. Okay. So as promised last time, I'm going to give a flavor of my own interest in mathematical research in quantum probabilities, so that you can see what is the research problem. After getting the answer to the problem, I will mention open question for future research. So if you can do that, I will be very happy. Okay, I do something, I leave something for you, and if you can do that, you can be promoted very quickly to full professor. So what is the motivation of study functional analysis? Could I ask how many people among you know functional analysis? A lot, right? But the question is, why you study functional analysis? What for? I think that most of the teachers in mathematics just teach and don't tell you why. Okay, and where it come from, and why it come from, and they say, oh, everybody study after real analysis, we study functional analysis, and that is the program in mathematics. No, everything in mathematics come from physics. We do that for physics, for our iPhone, for our GPS. Okay, on that one, we need to help engineers to design a system. Okay, so functional analysis was developed by von Neumann precisely to provide the language for quantum mechanics, because it's different from Newton mechanics. Newton mechanics, all you need is real analysis. But when you go into quantum mechanics, what is different, then you need another language, and that language is called functional analysis. Okay, so for example, basic quantum mechanics require mathematical structure such as Lie groups and representation. So if you are really interested in mathematics, here is a text that I recommend: Quantum Theory, Groups, and Representation by Peter Wood, just a few years ago. You go on Google, you get the ebook. Okay. Then all of this one, group theory is the main important thing. Okay, especially Lie group and so forth. It talk about how things moving. In Newton mechanics, when you have his second law, F equal m gamma, the force is equal to the mass times the acceleration. That the equation from Newton is called a law because it's confirmed. Okay, so how you get the how you design the airplane based on that law? You simply, it's a different equation. Then you do 2 times integration, you get a solution. Okay, so that is what happened. There's no really complicated motion. But in quantum mechanics, the thing is we don't see it. It's too small. We don't see it. That's why we have to try to guess what it is. And in order to study how things move, we need the algebraic theory of groups, especially Lie group. Okay. So in classical probabilities, the concept of conditional probability is essentially a variety. It's everywhere you need to do that. You need to use conditional probability in a lot of situations, including Bayesian inference, economic probabilities, reasoning, in decision making, expert system, everything. So in the context of reasoning toward decisions under uncertainty, classical decision theory is based upon probability logic, not quantum, classical probability logic. Von Neumann knew that very well. That's why after providing the mathematical foundation for quantum mechanics, that means functional analysis, he addressed quantum logic as well. So today I will talk about conditional quantum probability logic, and we will see why. So the motivation of the research is the following. There is at present an active research in the literature surrounding the concept of quantum probability logic in which the implication operator should be consistent with quantum probabilities. So implication operator is an if-then. Then you say something like this when you do mathematics. If f is differentiable, then f is continuous. That is your logic. Okay. The question is how you use proof by contradiction. So if f is differentiable, then it's continuous, and that is true. If you want to use contradiction, you say, I have a function which is not continuous. So what can I say? Then it is not differentiable. And that is correct only in two-value logic. Everything in mathematics is only true or false. There's nothing in between. Okay? Because there's no uncertainty involved when you do mathematics. But when you apply things to real things, if there's uncertainty, that logic has to be modified. Otherwise, you cannot get the correct result. So, and that is called implication operator. That means if something, then something. And the question is that statement is correct or not. However, a bona fide means legitimate. A bona fide quantum implication operator consistent with quantum probability, that means we use probabilities to represent the true value. You cannot say if you throw a coin, it will land head. You can only say if I throw the coin, I will get head with true value 50%. Okay, that's the difference between ordinary thing and thing involving uncertainty. So our research, joined with a colleague of mine, John Harding, aim precisely at providing a solution to this missing problem. They talk about implication operator, but there's no quantum operator consistent with the true value. And that is the problem of research right now in the literature. So we get the solution to it. And you will see it turned out to be amazing. It's very easy. And I don't know why they don't know. Okay, so our research, so the result is announced in the Google. If you click on Google and click on quantum conditional event, you will see a couple of things. In fact, I sent out another paper just appeared to Ajahn Terare already, and you think that you can have all the detail in that. So the outline of my talk today is the following. In view of current research interest in quantum uncertainty in social sciences, for example, economics, we address the open issue concerning the existence of implication operator in quantum probability logic, compatible with conditional probability logic, what is discussed in many papers, actually, like a paper just a couple years ago. They're talking about things like this, but they don't know what to do because there's missing implication operator in quantum logic. So I will, let's say I just say the talk will be a bit technical, but I will make sure that you get the point. So relax and enjoy it. I will try to proceed to make sure that everyone will have something to take home. Okay, I always say that. That means when you get out, I said, oh, you don't waste your time. You did have something, and that maybe you like it. You can explain to your friend, or you can go deeper into the topic. So first of all, in any logic, the implication operator is like an arrow, something. It's an if-then statement. So make sure that you know. That means if my function is differentiable, then that function is continuous. That is an if-then statement. It's an important operator in inference, and in logic, we call that modus tollens. Okay. In everyday in mathematics, two-value logic from Aristotle, the true value is only true or false. An event B implies A. Think about event B, a function is differentiable. and A, the function is continuous. So if the function is differentiable, then it implies that the function is continuous. This is equated with a connected, it's called a material implication. B imply A means not B or A. The prime is a negation, an element of the Boolean algebra of event. Since true value, these two things are equal because their true values are the same. So as such, mathematical proof by contradiction is based on modus tollens of material implication. And that is everything that we use in mathematics. But there is one situation I want to mention you quickly. You might hear if anybody do anything about mathematical statistics, you should be aware of the following. Mathematical proof by contradiction in statistics is wrong. Because they don't know that is not the same as the two-value logic. Probability logic means the true value are probability value. So probability value take every two value from 0 to 1, the whole interval, not just 0 and 1. This is a multi-value logic. So the logic of hypothesis testing based on something called p-value. The so-called reverse logic is an argument by contradiction. Richard Feynman, let me go back. What is that? Something. Okay. David Friedman said it loudly in his statistic book in the chapter, A Close Look at Tests of Significance. The logic of hypothesis based on p-value, the so-called reverse logic, is an argument by contradiction. This sounds so impressive, and there is so much mathematical machinery clanking in the background that tests seem truly scientific even when they are completely nonsense. Science theory understood this kind of problem very well. When a mystery is too overpowering, one dare not disobey in the book, in the little book, The Little Prince. That means they talk too much. You cannot check. Then you have to follow, but it's wrong. If you dig into it clearly. So here is the situation. In two-value logic, why if the function is differentiable, then it is continuous. And then if you want to show, then if the function happen to be not continuous, then you can deduce that it is not differentiable. Why? It's because of this. Okay? If you say B imply A, that means the same thing as not A imply not B. Because this is the rule in Boolean algebra. So in reasoning with probability uncertainty, we use probability logic. The syntax remain Boolean, whose two values space is the unit 0, 1, rather than just two values 0 or 1, an analogy with fuzzy logic of Lord Pizzade in 1965. What is the implication in probability logic? The reason I go in this, because my purpose is to answer this question for conditional quantum probability logic. But I just said to you that nobody knows. It turned out to be easy. The reason is this. I have already looked at this problem for classical probability logic 30 years ago. They don't look at that, so they don't know. So I will use my old result and to get the new result from classical probability to quantum probability. So the question is, what is the implication in probability logic? Well, George Boole is, George Boole is the father of logic and at probability. He write about the book, an investigation into the law of thought. That we have everything like a Boolean algebra, Boolean sigma field, everything is from him. But he make a mistake at helping recall. Unfortunately, he, Nguyen Boon, confuses the probability of a conditional, which is material implication, with conditional probabilities. And solve not the stated problem, but one involve conditional probabilities. But interestingly, Boon mistake is a good mistake. Ajahn Teradet, when you do a mathematics, do you make mistake from time to time? Everybody make. But the question is, the mistake is the good one or the bad one? Remember last Fermat theorem. You know how they solve the last Fermat theorem? Because of a good mistake, a Japanese mathematician said thing that he proved last Fermat theorem and published a paper. Turned out to be wrong. You know what he did to himself? Harakiri. He killed himself. Because you have to know the following. For the Japanese, the most important is shame. Shame, you cannot live with shame. If you think it's so shameful, you have to kill yourself. Okay? The good mistake, because the good mistake in last Fermat theorem, that finally will get the correct one. And here is what exactly the same thing that we get. The Boon mistake turned out to be the right thing to do for probability logic. He was basing if then on something wrong. That is only valid for two-value logic. But the logic he's considered is not two-value logic, it's the probability logic. That means when you say something, is that true or not? You cannot say true or not. You can say, what is the chance that is true? That is a probability logic. So it was Boon's mistake with Les Stanlaker in 1970 to put down a thesis, that means like a hypothesis, that in probability logic, the true value of the conditional if then should be conditional probabilities. That means A imply B, the probability of A imply B have to be the conditional probability of A given B. But you can, so this is the equation. So if I give you the value probability of A and B, can you get for me the solution? This is the equation. So how you get, what is B imply A by itself? If I give you the value of conditional probabilities. Okay, now clearly, if you look at that equation, this cannot be classical implication, because if you compute the probability of the classical material, you get something bigger than conditional probability. So it cannot be equal. So this is not a solution. So the question is, what is the solution for this equation? What is the solution for this equation? You know very well, Ajahn Tira, that suppose you have a quadratic equation on the real line, and you want to find out a solution. If it has no solution, then what? You go to complex number. Then you have solution. You make it bigger. The real line is just a line, but the complex number is like the whole plane. So if you don't have solution on that space, you can get a solution outside of that space. And that is a basic in mathematics. And we do that all the time when we need a solution. You have an equation, quadratic equation, ax squared plus bx plus c equals 0. And you want to find out a solution. And turn out that's no real solution. It always has solution in a complex plane. And that's what I'm doing here is exactly the same. First of all, in fact, there's a theorem. Well, theorem would say that that is no solution. That equation will never have a solution. If you're talking about the solution should be an element in the Boolean algebra A. So the question is, in 1988, a friend of mine, Goodman, and myself, we offer a solution, just like a complex value for equation. And that solution is simply this. We are going to describe briefly the non-Boolean solution of the problem, which will be served as the backbone to obtain the counterpart in quantum conditional logic. That means the quantum probability logic in which quantum negation is not the Sakaki hook. The Sakaki hook, I will mention later, is the materialization in quantum logic. Okay, there are three things, don't forget. Quantum logic is two value. And then quantum probability logic is multi-value. And then quantum conditional probability logic. So we are going to use, and that will use the concept of Lerner rule that I mentioned at the beginning. So it is amazing that researchers in quantum logic and quantum probability logic seem not to be aware of the corresponding issue in classical probability logic that we solved already many years ago. So here is the Sakaki hook. The Sakaki hook, let me see the Sakaki here. So let's, for our work in the 1988, if you want to see, there's every book. But a comprehensive survey of what Goodman Nguyen work is in a famous paper in the journal of British Journal of Philosophy of Science, Bruno de Fenety and the Logic of Conditional Event by Peter Nguyen. In other words, we are going to give you the solution of this. It's a non-Boolean. That means it's not an element in the Boolean. What is a Boolean algebra? Boolean algebra is like a subset of a set. It's called a Boolean algebra. Okay, a Boolean algebra has operation, union, intersection, and complementation. That structure is called a Boolean algebra in logic. Okay, so it is easier to change Boolean algebra into Boolean ring. So what is a Boolean ring? A Boolean ring A is a set would have two operations on it, multiplication and addition, just like the real life with multiplication and addition. It's a ring with unity 1. It has a 0 in which every event is idempotent. That means your A times A is equal itself. And so the intersection, we are seeing that AB will be either Boolean event or projection on Hilbert space, depend on we're looking at ordinary event or quantum event. So we have a structure that we can manipulate easily. So we look at the solution, and the solution turned out to be this. So I give you the answer. The solution is, the solution of the equation is this coset in a Boolean ring. Okay, this is a coset of a Boolean ring, and so the collection of conditional event is a collection of every element of this form, would turn out to be very simple if you use a equivalent representation. So what is, if you look at the equation, Let me show you the equation, and I can tell you what is the solution. If you look at this equation, okay, you look at the equation. I give you the conditional property of A given B. And I ask you, what is B imply A? You know what is it? It's just a pair A and B. A and B, but A is smaller than B. So it's two things. So it's not on the line. It is a complex plane. If you take this to be a pair of AB such that A less than B, what does that mean? A less than B. That means if you talk about subset, then A is a subset of B. If you talk about quantum event where A, B are projection. So what does that mean? One projection is smaller than another one. That means A is less than B if B minus A is a positive linear operator. So everything can be done. Okay. So we can have that solution. So once we have that solution, then we can go into, we solve our problem completely. Now let's talk about quantum logic now. Quantum logic of von Neumann is a two-value logic. Something is true or false, nothing in between. It's a true or false. But only extending Boolean algebra to a lattice. The reason is this: in classical logic, we have a Boolean algebra, event as subset. But in quantum setting, event are projection on the Hilbert space. So they don't have intersection. So, but they have a multiplication. You can, like a two matrices, you can multiply. You cannot take the union of two matrices. It makes no sense. Okay, but you can add two matrices. You can multiply two matrices, and that is called an automodular lattice. A lattice would has come out from a partial order. That partial order is partial order among projection. So I repeat, a projection A is less than the projection B if B minus A is a positive operator. Everything is just fundamental in functional analysis. Okay. Now the implication operator in quantum logic is called the Sakake hook. Here's the notation: A imply B. It's not material implication. It is a material implication only if A and B are commutative. Don't forget A and B, just think about A and B just like two matrices. When you have two matrices, sometimes A multiplied by B equal B multiplied by A, but not all the time. When that happens, the two quantum events are called commutative. And this is the Sakake hook. So the question is, what is the probability of what is the quantum probability of the Sakake hook? Is that equal to the conditional probability of A given B? So the question they ask and they doing right now is exactly like in the classical case. And we already solved it, but they did not know. So we don't need much to give them the answer today. So quantum probability now is, remember last time we said, omega AP classical probability is translated into the triple called the quantum probability space, where H is a Hilbert space. We need Hilbert space for projection. If there's no Hilbert space, there's no projection. Something orthogonal to something else, we need inner products in order to do that. That's why the first postulate that I mentioned of von Neumann in quantum mechanics, a state of a quantum system is a vector of a Hilbert space. L is the collection, what we call quantum event, and they are nothing else than projection linear operator from A to H, but projection. Okay, that means it have to be self-adjoint, have to be self-adjoint and idempotent. You do projection, you do it 2 times, you stay right there. And rho is the state, play the role of probability P in the classical case. It is a matrix with unit trace. Don't forget, in quantum mechanics, trace replace integral. There's no integral. Trace replace integral. Because integral cannot be on infinite dimension space. There's no measure on infinite dimension space. Everything you do real analysis, the dimension of your space is finite, like R to the N. Okay, but N is finite. But Hilbert space here is the space L2 of function solution of the Schrodinger equation. So it's infinite dimension space. It's Hilbert space. Okay, so rho either is the operator, which is a positive operator with trace equal 1, or equivalently, rho is an element of the Hilbert space with norm equal 1. Extending, then if you have a quantum probability event A, what is the probability of getting that event? That means P probability when the system is in the state rho of the quantum event A is equal to the trace of P of rho time A. Don't forget, the trace operator is symmetric. So it doesn't matter. You write rho A or A rho, it's the same. So there's no confusion here. And that is part of Luder rules that we come to now. So quantum conditional probability is defined using Luder rules, which reduce to classical probabilities for quantum event. And here is the formula. You can see, think about this. If you look at this, you think about A is an event in the classical case, B is not an event. And here is the probability of the probability at the beginning, rho. So what is conditional probability of A given B classically? You will say probability of A given B equal probability of A intersection would be over the top of B. So the conditional probability of A given B is the same as probability of P of A intersection B given B. And that's what it is. Translate into trace operator. And this is called the Luder rules. And that is a postulate. But it has a reason why it is so. Because extend clearly what happened in classical logic. Because you know why? Because if you have A less than B, then they are commutative. But if they are commutative, then everything goes through. They are commutative, we are exactly like in the case of classical probabilities. That's why the formula is justified. Because if A and B are not commutative, then what happened? It doesn't matter, because probability of A given B is the same as probability of A intersection B given B. But A intersection with B is inside B. That means this equation is true in general, not only for commutative event, but for all kinds of quantum event. So this is the so-called quantum conditional probability formula, and it come out from the Luder rules. So let's go to the main point now. We're talking about quantum conditional probability event in quantum logic. The problem of quantum implication, don't forget, everybody doing in computer science, if they try to write out quantum algorithm in order to put into quantum computer, they need on this. Because they need Quantum mechanics is based on logic. Algorithm is based on logic, not theorem. They have to know the logic in order to do quantum computing. So the problem of quantum communication in quantum conditional is exactly the same as classical logic. They did not know that. That's why they keep asking and showing things and still end up with nothing. And that's why we propose to do the same thing at Goodman and Nguyen. We did it over 30 years ago. But for classical probability, I did not know quantum probability at that time. I heard about that, but it's not my interest. I am interested in quantum probability only 5 years ago when I met people at the conferences and they said, oh, we use quantum probability now, not only for quantum computing, but for psychology, decision theory, human make decision. They don't use ordinary probability. There are so many contradictions. So finally, they find out that quantum probability is good for economics. In economics, you make decision like invest, financial economic. When you make a decision, you are a person. And there are uncertainty. You invest, you want to know how much you might lose. And that you have to do how I diversify my investment so that to minimize the risk of losing money and things like that. They use probability, ordinary probability turn out to be not correct. And then finally, they figure out that quantum, because people don't use commutative and additivity of probability when they make decisions. And that's why I'm interested from that time. But I did not know this problem until last year when I just happened to look around and see that, oh, this is very easy to get one, how they don't do it. So we have to do it. So you can see our approaches follow. Details are given in our paper. I mean, in the conference proceeding. That means the Thailand conference of econometric in Chiang Mai last year. Okay, let me see. Okay, so here is interpretation. Interpretation is very simple. The set of conditional events is just like an ordinary one. That means equivalent to a conditional event of A given B is simply a pair of A and B where A is less than B. In Boolean logic, less than means a subset. A is a subset of B. But in quantum probability, there's no subset because A and B are projectors. They are linear operators from a Hilbert space into itself. So less than means A less than B, means B minus A is positive. Positive in the sense it is a positive operator. So everything makes sense. So everything you can do on this simple representation, and you can define operation and go back to the conditional event, and here are the operator. A and B is one conditional event. But what is that? That is the if-then rule. If this is the if-then rule in quantum logic. Okay. So you have an if-then rule, you can, and this is basically the reason that we did that long time ago is because in 1975, you know what happened? The new thing come out, expert system. Expert system come out, rule-based system come out in 1975. And they need to know if you have if A and B, if the rule, there are rules, okay? For example, for a medical doctor, what is the expert system in medicine? For example, the rule is like this. If the eye of adjunct Teradet is yellow, then he has a liver problem. Okay, that is the rule. Okay, a doctor have a system like that. They have a by experiment. Yellow eye, if someone have yellow eye, you have to look at his liver. Okay, because most of the time the liver have problem, your eye become yellow. Okay, so they have rule like that. But is that true? Not 100%. Maybe 95%. So they have to use logic of conditional, but classical probability, they're still using it. That's the reason why we're looking at this one around that time. So we get exactly the same thing. We get exactly the same thing again, only with one exception. The conditional probabilities in quantum logic is the new one, which is the one given by Luder rule. But the syntax underneath the problem of implication is the same. So they ask right now, if you go into the Google and you click on the topic, quantum probability logic, implication operator, they are still asking, what is that? We don't have it. So I tell them, if you have two projections, if you have, what is the conditional probability of A given B when A and B are projection? And if you want A and B at a bona fide mathematical entity, what is that? That is simply a pair of two projectors, but one is less than the other one. And if you assign the quantum probability on that, it is consistent. That means it give them complete solution for the equation that they don't know how to solve. It turns out that equation we solved already 30 years ago, but for classical probabilities. And there's no difference for doing that for quantum probabilities. So that is the main thing. I just go quickly for the problem for future research. Okay, this is the problem for future research. We can. This is what we get. This is what we get for classical probabilities. Already get. Okay, we already said the solution for this equation, probability of P of B imply A equal classical conditional of A given B is a pair. But a pair is not an event. So is that possible to get another solution, which is a little better? That means it is an event rather than a pair of events. And here is our solution. Okay, you start out with the probabilities by omega AP. So first of all, you extend this one. On omega star, the product, infinite product, but countable, of the space omega. XOA omega n is the same as omega. You multiply this 1,000 times. And let A star be the usual product sigma field of that product space. That means the one generated by the cylinder of the following form. This is a classical measure theory. And then how about P? The probabilities is simply, the probability is the same. Probability omega become omega star, infinite product. A is the sigma field of this, and P is the product probabilities on this space basis. So that means rather than embedding, we're extending this probability to an infinite probability space. Then define a map from A cross A ordinary to the infinite thing by a formula. And it's a very funny, I leave there for you to check. But if you compute the probabilities of that using, you get a geometric series. You get a geometric summation of something right to the end. And you know what it is? Okay, so this one is equal to 1 over 1 minus quantity of P prime, and you read that it is precisely the condition of properties. This is a big result, surprising, but it's a good one. And right now the question is, can we do that for quantum properties? How can you do all that with event? Well, here is a set, ABR set. Can you do all this with AB operator projection? That is an open problem. Very interesting, very important. And here is the hint for you. But we don't have time yet. A possible version of the above product property space technique could be based on Fock space or countable tensor product of Hilbert spaces. Rather than product like this, you take tensor product. Okay, so that is what we think. Okay, and I don't know, I don't know if I have time to do that or not, or thing, but I think that we put that on Google, so see what happened. Okay, I think that so let me summarize. Let me summarize before a question. You can see the problem is this. You want to find out a model stolen for conditional quantum probabilities. And that is very basic for many things, but mostly for quantum computing. Okay, so what does that mean? If you say a projection A imply a projection B, what is that? What is that a projection? If you have a projection A and B, you multiply, or you get another projection. Okay, you subtract the two, you might get another projection. Okay, but what does that mean? The projection A imply the projection B. So that when you compute the quantum probability of that thing, it is equal to the conditional quantum probabilities. We just solved that problem. Okay, so they can use that one to when they have to take something in quantum connected in any logic is the implication operator that allows you, for example, to prove thing by contradiction. Okay, so I think that we have 15 minutes or so for questioning. Professor Songpong, you might give me some difficult questions.
Okay. May I, Dr. Tirde?
Yes, yes.
Actually, Dr. Hung,
Yes.
I have many questions, but I will talk with you via email. But for now, I would like to thank you for very beautiful mathematics and a very good talk. And I feel like I have something to take home.
Yeah, one thing I have to apologize for everybody is I don't like, but not many often to give a talk like this. I always do on the board, writing. So it's very clear. It's very clear one thing, you know, anything there, and you can prove that thing. But on Zoom and giving, if Ajahn Tara give me 3 hours, then I will use the iPad and writing. Just like I teach courses in Chiang Mai. Every class is 3 hours. Okay, so I hand out things like this for them to read. They have it, but I will cover everything on writing for them to stop and show everything clearly on that. So a little sloppy by talking about things and without really mentioning things. But what is interesting, Professor Songpong and others, one thing is very important. When people in computer science, they know why they need to know something in mathematics. Okay, they know very clear because they are going to write algorithm and using computer thing like that. But for mathematics alone, sometimes you learn things if you understand and know why you study this and where it come from, a little history and thing. That's very interesting that you can see. So you can see here on the mathematics, it's not, see, it's little, this is not functional analysis, okay? This is the probability, you know, but the context of it is logic, that's all.
Dr. Huang,
Yes.
can you write down a manuscript or lecture note on this talk so that we can read, write down in details?
Oh, Ajahn, I read that, but I think I sent to you too. I send you an additional reading
Yes, in
about
the
this
chat.
100. Please send to Professor Songpong everything from A to Z, about 200 pages. I send it up. Everything about condition, functionality, background, C-star algebra, everything, and including something that you might. I want to ask you one question. Why the moon doesn't fall to the earth and the apple fall? I explain everything in that. Why a person on the outside of space, it's a wavelet, right?
Mm-hmm.
Why is it wavelet? It's not wavelet. You know why it's wavelet? Because he's falling. He's falling down. That's why he loses on the power. The moon falling into the earth, falling, but not to the earth, around the earth, because of the curvature. Just think about an airplane. Why the airplane doesn't fall? Ajahn, why the airplane can fly? He doesn't. If it fall down or not, it's landing. They do it. Why they can tame the airplane like that? So I mean, things like that is very interesting, and I think that things like that, all of that, are in my additional reading. Yeah, additional reading, including the two papers about this one, Professor Songpong. So if Ajahn please send everything you have to the Songpong.
Yes.
Yeah. Okay. Other questions? I want to hear a question about this or anything related.
I think your work with Goodman is when you work for the U.S. Navy, right?
Yeah, we do that.
Because I look at the Google, it's from the U.S. Navy.
Well, there are two books, huh? I wrote two books on it. Book, huh? Okay, there are two books and a lot. It's called measure free conditional thing. Okay, no, yeah, but this it's just an accident, you know. I'm not doing this for a long time. It just happened that when people talk about right now, even economic is quantum economic, psychology is quantum. That's more than just quantum computing. So if you happen to like this stuff, and suppose that you happen to say, oh, I heard a little bit from Ajahn Hung about quantum probabilities, and I am a probabilist. I want to do some research in quantum probability. I hope that with everything I send out, you know why and what for. Clearly, everything. It's not. Then it boils down to dig into. I recommend a couple of books already. Look into the calculus of probability, quantum calculus of probability. Classical is real analysis. There's nothing more. But if you want to do quantum probability, it's a functional analysis and C-star algebra. So you know that, oh, because I know this, that one make me learn about C-star algebra. So mathematics is a lot, but if we don't know what we're looking for, you know, there's no incentive to study. But after this, you will appreciate what is the spectral theory. Why is spectral theory invented by for Neumann. But it doesn't come from nowhere. It comes from something we know very well for 2 centuries. You know what? Matrix algebra. Functional analysis is simply infinite dimensional version of matrix. But matrix has something very interesting, non-commutative. Non-commutative algebra. And that is needed for quantum mechanics. We ordinarily, we do algebra, we always like things with is commutative. Otherwise too complicated. You know, AB is not equal BA, thing like that. But when we talk about matrix, we use matrix to do something, but we are not looking at matrix from a logical point of view. Okay, now we must, because that happens to be precisely what is needed to represent quantum logic. Because they are operator. Matrix are operator in finite dimensional space. So if the space is infinite, then what is a matrix? You don't have a matrix with infinite thing. And that is an operator. It's a linear operator because a matrix is the operator. So it comes to a linear operator. So everything matrix, everything you have a matrix, you can simplify it by either by singular value decomposition. That means you're looking at the eigenvalue and write it down. And that in matrix is just fine. That's why, okay, I want to ask Ajahn Sompong or Ajahn Tore, why we know that the Earth go around the Sun in an ellipse and not in a circle.
No answer.
Well, you know, who did that? Okay, who said it's Kepler? Kepler, he long time ago, there's no satellite, there's nothing. When Copernicus said the following, the Earth is not the location of everything. The Sun does not go around the Earth, but the Earth go around the Sun. He said that without seeing anything. Turned out to be true. Okay, and then the guy from Australia, Kepler, said the following: how the Earth go around the Sun? He didn't see anything, and he said, no, it does not go around the Sun in a circle, but in an ellipse, because of the spectral theory of matrices. It's called the theorem of principal axis. You change coordinate, you make a rotation of 45 degrees. If you have an equation, you change it, you can see better the form. And when make a rotation of 45 degrees, they find out that it's an ellipse. It is true. They don't see anything. Only mathematics working in a dark room. And they find out that the Earth go around the Sun. And then Kepler said more than that, right? Kepler has 3 laws, okay? The Earth goes slowly when it's far away from the Sun on the ellipse, and faster when it's close to the Sun. And the Sun is not at the way the Sun is one locus of the ellipse of the orbit of the Earth. So, you know, so I just want to say that it's interesting that when you learn, let's say, functional analysis, showing many difficult theorems, it will be interesting to figure out, you know, why we're doing that. Okay, any other questions? Okay, one more thing, Ajahn, because you take care of the.
I have a question. Can you explain?
Oh, there is so many. Okay, go ahead.
Slide 16. Slide 16. And the equation. Can you explain more?
What equation? What equation? Show me. Tell me. Stop me.
16.
There's no page. I don't have page. Yeah.
You look at
okay,
the number.
More.
Page 17.
This one? No.
Back.
That equation?
Yeah. That's this equation.
This equation, huh?
Yeah.
Okay,
Yeah.
that's the main equation. Okay, I have think about AB event. Okay, subset. Okay, think about event. This is the probability of B imply A is equal to condition B. The one on the right, you know what it is, right? Probability of A given B equal probability of A intersection B over probability of B. That's what you know. This is the known. Okay. The thing over on the right is known. The thing on the left, we know what is P, the same P. But the thing inside, B imply A, that means the implication. Okay, the implication. So the question is, what is B imply A? So that its probability is equal to this. That's the equation. Just like you have equation x squared equal 1. 1 is known, but you don't know what is x. So what is x, right? Just like that. So this is an equation. The problem is how you define the solution of this equation. What is B imply A? In classical logic, we had a solution. Okay, I give you the solution in the classical logic. Where is that? Okay, here is the equation that we have the solution, just like equation of quadratic. Okay, here is the solution. B given A is equal to not B or A. That's the solution. If you're talking about true value logic, true or false. Okay, look at this one alone. Only these two last things. So B imply A, that means if B, then A. And that is this element, not B or A. Think about it. Take an example. Take an example of thing. Okay. B. Yes.
We look at the set, or we look at true or false. B at the true value or false value, or B is a set, A is a set.
Yeah, here this is equal to this. If we are talking about two value logic, think only true or false. There's nothing in between.
Okay, thank you.
Okay, so you can think about this. Just do the following. Take B equal, the function is differentiable, and A is the function is continuous. Then you have the following. If B, then A, and that the true value is 1, because it's true. And you look at this event, not B is a differentiable. So B prime is not differentiable or continuous. It's the same because the true value are equal. When true value is 1, this is also equal 1. When it is 4, this is also 4. Logic is looking at true value. Okay, so we have this solution for the equation. But this is the solution, but it is not equal to the conditional probabilities. So if you take this as a solution, it is not a solution of the equation that we're looking at. It's not a solution. Okay, it's not a solution. It's not a solution because you can see, okay, this is equation. If you take B imply A at the solution we have before and plug in here and compute the probability, it's not equal to this. That I already show here. Where is that? Okay, do I get that? Maybe before. I show something that it's bigger. It's smaller than conditional probability or something. Okay, I should let me show that. No, where is the one? Okay, let me see. Maybe down here. The probability of that is different. Where is that? Right here.
Yeah,
You
yeah.
see, if I this is the if I then be if you take this to be this, then the probability of this is bigger than this one, not equal. So it's not a solution. You want to have something that when you compare with it, it's equal to this. Okay. So I look. By the way, any other questions? By the way, Ajahn, I look at your list of previous seminar. I heard someone have talking about optimal transport theory, right? You can talk about that. Yeah. So I just want to know. Just want to tell you in case that you need me. Okay, always happy to do anything for you know for free. Okay. My interest
very
right
much.
now. My interest right now is optimal transport theory related to this too, because the conference in Chiang Mai in January will be optimal transport for machine learning with application to economic and things like that. Right now, we are doing quantum probability for optimal transport. I think that optimal transport that everybody doing PhD in mathematics or things like that is involved very much in optimal transport. Optimal transport is a little less sophisticated than that, because the mathematics is only partially functional analysis, still basically measure theory and things. So sometime if you have people interested in topic or research in optimal research, let me know. Is anything on the chat? No, I don't see anything. Nothing on the chat.
No.
So, okay, any question? A few more. Professor Songpong has a lot. I want to. Did you get something to take home? Okay, that
Oh,
one.
a lot.
Yeah, I just say that because one thing I always want to advise students: you need to look. You have to take a course or read a book in logic. You use logic everywhere. You don't know what is logic. Okay, the first course when you get into math, if you get into university, the first course to take is logic, and then you can take calculus and everything, because you don't remember. Not only that you do everything by logic, but even in mathematics, when an Ajahn show you the proof of a theorem, how you know that his proof is correct? You follow the logic what he's doing. Okay, you follow the logic of what he's doing, and that logic is very simple. It's only true or false, nothing else. If it's not true, then it's false. Okay, that's nothing else. But we are in a situation when you do mathematics for real application. Everything we run into are random, except two things. You know what are the things that is very certain? Death and taxes. That is a famous quote from the author of the book Robinson Crusoe. That you know that. He said everything in life is uncertain, except you must die and you must pay taxes. So everything you do with that, you cannot use two-value logic anymore. When uncertainty involved. Last time I said the following: when they discover that probability is needed for quantum mechanics, Bertrand Russell said the following: probability is very important for science, but nobody understands what it is. It's true. When you say if you ask, if I ask Ajahn Tirade, what is the probabilities that you will have a car accident on the street, and how you answer that, and how you compute that? You say,
I don't know.
if you say 60%, what does that mean? That means among 10 times, only 6 times is correct. But you never repeat. If I ask my question, what is the chance that I will die next month? Professor Songpong will say, that is like a 5%. What does that mean, 5%? That means if I try to die 100%, 100 times, 95 times I will alive. But I don't repeat. I cannot try to die for him to count. See, we use every time we don't understand the meaning. That's why we need to use that. Okay, we need to use that in order to have an idea, to help things, to make. But that is useful for decision. Even we don't understand what it is, it's useful for decision. Suppose that you say, if I invest here, the chance that I will lose money is 80%. Then you don't do it. Right? Then, okay, I don't understand what does that mean 80%, but it helped me. It helped me to make decision that I will not invest. Okay, but one thing is important is mathematics. Doing on this, we need to help people. For example, quantum computing engineer. They follow the rule that we tell them. Okay, so like engineering, how you make an airplane, the physics had the law, but the law have to be implemented by mathematics in order to do that. Okay, so it's so enjoyable if we know what why we do certain things. Okay, it's
Okay.